Welcome to SysN 5470. I'm going to be walking you through this explainer for Case Study 01, Build a Network. Since you're going to be tackling this independently over the weekend, we want to get you perfectly oriented so your time is highly focused. Let's just dive right in.
So, imagine a severe storm just hit. The Emergency Operations Center, the EOC, is scrambling. They need to answer one incredibly urgent question. Who can still communicate with whom? Now, if your first instinct as an engineer is to open a massive spreadsheet and just start doing manual lookups and table joins to trace that communication chain, you're going to fail. Honestly, that messy reality of relational communication data, it's practically impossible to untangle with just rows and columns. You're just guessing until a critical link breaks and it's suddenly too late. This case study is the direct engineering response to that exact scenario. Throughout this course, we're focusing on building 4 concrete professional skills. We've got identify, measure, infer, and predict. For this case study, we are entirely focused on skill 01, identify. The absolutely crucial takeaway here is that you've got to learn how to frame messy relational data as a graph that actually answers a real engineering question. Recognizing that your system problem is, at its core, a graph problem, that's the most critical step you'll take. And this mental framing has to happen long before you ever write a single line of code. All right, this is where we deliberately slow down. This is your sketchpad moment. I literally want you to grab your notebook and a marker right now. Seriously, grab it. I want you to feel the tactile difference as you draw this. First, just draw 2 circles, those are your nodes, and connect them with a simple undirected line. In an undirected network, that tie just means they communicate at all. It's a general relationship. Okay, now right below that, draw 2 more nodes, but this time connect them with a directed arrow. That represents a directed network. Here, an edge is a specific operational channel from a sender to a receiver. Think about it, a shipment of parts is directed, right? But co-membership on a safety committee is undirected. The actual engineering thinking happens right here on your sketchpad. The software tools you'll use later, those are purely for verification. Next up, you're going to step into the interactive browser-based playground. Now, don't let its visual simplicity fool you. You're going to rely on 3 basic actions to build your models here. Number 1 is select, where you'll inspect nodes and drag entities around the canvas. Number 2 is add node, literally dropping a new entity right into the system. And number 3 is add edge, connecting a source directly to a target. Building things this way brilliantly illustrates the core lesson of the lab. As you physically draw that node link diagram on the canvas, the underlying edge tables and the adjacency matrix are updating instantly, in perfect sync. You're going to see firsthand that a network is its edge list and its node list. The picture on the screen is really just one way to view it. Let's see exactly how that applies to your first learning check. I'll just sketch the scenario out for you aloud. Imagine an island electricity grid. You've got one main generating station that feeds 3 transmission substations. Substation A is responsible for feeding the North District, the Downtown District, and the Hospital District. Meanwhile, Substation C is being held in reserve as a backup bath. You're going to build this exact network in the interactive playground. Your task? Find the hidden vulnerability. If a station failed, what would break the most connections? And I'm intentionally stopping right here. No spoilers. I'm not giving you the answer. You're going to use the adjacency matrix in the tool to figure that out yourself. Once you've solved that manually and really built up that intuition, you'll move on to the code phase. You'll open either the example.r or example.py file in your workspace, depending entirely on whatever language you prefer. You've already done the conceptual heavy lifting on the sketchpad and in the playground. Now you're just going to let the code handle the heavy lifting of scale. We're providing a dataset for a synthetic bipartite supply network. We're looking at roughly 80 suppliers, 120 components, and about 600 edges linking them all together. The code is going to show you exactly how to pull this tabular data and construct a graph object that you can actually run computations on. Before you start, we need to completely dismantle a core misconception right here and now. Listen closely. A network is not just a picture of stuff connected to stuff. That massive visual hairball of dots and lines you always see in corporate presentations, it largely doesn't matter. What actually matters is the deliberate engineering choice you make about what constitutes a node and what counts as an edge. And that choice is based entirely on your specific operational question. A network is an operationalization of the problem you are trying to solve. Nothing more, nothing less.